Greetings and welcome to another installment of Quant Slob. This time around, we're going to take a little break from our ongoing mini-series hypothesis testing of a single proportion to bring you the Marilyn vos Savant drama. This is our second purely topical video here on Quant Slob, the other, of course, being our Simpsons paradox video. A more scholarly title for this video might simply be the Monty Hall problem. But we chose our main title here out of deference to Miss vos Savant, and also because drama is really a very appropriate word to describe this particular piece of history. I want to mention that there is a really excellent article written by Zachary Crocket for Priceonomics. The link is in the description, and it is highly recommended reading for anyone even slightly interested in this story. It was very close to 30 years ago that Miss vos Savant became embroiled in one of the most fascinating and even perplexing episodes in the history of modern statistics. Now, Miss vos Savant was something of a wonder kid, like a child genius, somewhat reminiscent of the chess grandmaster Jose Raul Capablanca and the great mathematician Srinivasa Ramanujan. All three, at a very young age, showed genius far beyond their years. In 1986, Miss vos Savant began writing a column for Parade magazine titled Ask Marilyn, where readers would ask various types of scholarly questions and puzzles, and Miss vos Savant would respond with a solution and perhaps some commentary. The Monty Hall problem is based on a game that appeared in the game show Let's Make a Deal, which was hosted for almost 3 decades by Monty Hall. In real life, if you can call a game show real life, this particular game appeared in a number of variations. The so-called Monty Hall problem, as it is known, is based on a specific flavor of this game, and it goes like this. A contestant would be presented with 3 doors. Behind one of the doors is some very desirable grand prize. Of course, the contestant would not know which door and would choose one of the 3. The host would then reveal one of the 2 remaining doors that does not have the grand prize, and the contestant would be asked whether or not they'd like to switch their choice of doors. And so the Monty Hall problem asks, assuming we want the grand prize, are we better off switching or keeping our original selection? By the way, on Let's Make a Deal, they would place sometimes a zonk prize behind one of the other 2 doors, like a goat, and I guess they did that to make the contestant feel especially humiliated if they lost. Anyway, so it was this question, sort of, some 30 years ago, that a reader of Parade magazine submitted to Ask Marilyn. It is important to note here that the solution to this problem had been known for many years prior to 1990, published and discussed without fanfare and without any sort of controversy that I'm aware of anyway. So Miss vos Savant replied, and I'm paraphrasing, that yes, you should switch. By doing so, you improve your chance of winning from 1 in 3 to 2 in 3. This is and was generally regarded as the correct answer. Very neatly and concisely articulated for the reader, simple as that, and so of course everyone just gets on with their lives. Well, not quite. And by the way, if you've ever watched our Simpsons paradox video, the answer is yes. I've definitely got Miss vos Savant here volunteering to make a keg run. What in fact ensued, instead, was a hailstorm of rebukes and rebuttals. Mr. Crocket, in his aforementioned article, uses slightly more colorful language to describe the kind of storm that ensued. When I say hailstorm, we're talking literally thousands of letters, and so as if that is not bizarre enough, many of these rebukes originated from very high-standing academics and professionals, and some were, I think, unnecessarily vitriolic, and some of these letters to the magazine really smacked loudly of scientific dogmatism and chauvinism. And to be very candid, this matter of scientific dogmatism and chauvinism is not one upon which I'm really qualified to offer an authoritative exegesis. I am, however, prepared to explain solving the Monty Hall problem. And I want to offer 2 highly conceptually related ways to solve the Monty Hall problem, both of which evidently flummoxed Miss vos Savant's detractors some 30 years ago. You should be able to access some code examples in the discussion to simulate the Monty Hall game. And we can also formalize the solution by crafting a so-called probability space. And we're going to save this for a future video. Enumeration. Enumeration is like the preschool of probability theory, or more accurately, really, it's sometimes viewed that way, much too juvenile for any self-respecting probabilist, but it works great for problems like this. It turns out, in fact, we can reduce this enumeration by employing a simplification rule, and that is, we will always start by picking door 1. Each of the 3 rows in our table here reflects each possible location of the prize. Determining whether or not our original choice wins is very direct here. We can see that in the table. We need to determine the consequence of switching. Well, if our original choice is correct, then switching must lose because neither of the other 2 doors has the grand prize. In the second case here, the second row, the host must reveal door 3. Therefore, switching means that we will end up with door 2, the prize door. So we win. And the exact same logic holds for the third case here. Our simplified enumeration reveals that if we stick with our original choice, we win 1/3 of the time. However, switching wins 2/3 of the time. Okay, now, if we want to run with the big dogs, we'll need to come up with a symbolic solution. And of course, you know the Slav nation deserves nothing but the best, so let's give it a go here. It turns out, with the help of Bayes' rule, this is barbarically simple. So much so that it might even be said that this solution may be seen as deceptively difficult. Okay, so you can see we've got these 2 nice random variables here, x and y we're calling them. For both, the domain contains 2 elements. What we seek here, of course, is the probability that we will win by switching. Of course, we already know the answer to this, but let's pretend we do not. What do we know? Well, we know that the probability of our original selection, the probability that it's correct, that is wins, is 1/3. And equivalently, the probability our original selection is incorrect, does not win, is 2/3. So how do we proceed here? Well, it turns out that we know or can easily determine the conditional probabilities. And we actually already did this during enumeration. If our original selection is correct, winning by switching is an impossibility. We will end up with one of the 2 doors here that do not have the prize. Therefore, the conditional probability win by switching, given a correct original selection, is 0. If, on the other hand, our original selection is incorrect, winning by switching must occur. No matter what, we will switch to the door with the prize. Therefore, the conditional probability win by switching given an incorrect original selection is 1. So our system, or space if you prefer, is fully defined. We know everything there is to know about it. The probability of the joint occurrence of win by switching and a correct original selection is equal to the probability of the conditional weighted by the probability of the condition occurring, and same for the probability of the joint occurrence of win by switching and an incorrect original selection. And we finally get to our sought marginal probability by summing over x and arrive at 2/3. When we defined this game a moment ago, we said something like, the host then reveals one of the 2 remaining doors that does not have the grand prize. In the rigor of mathematics, this statement is unconditional, meaning that the host always reveals one of the 2 remaining non-prize doors. However, if this is not true, for example, if the host only offered the opportunity to switch if the contestant's original choice was correct, then, of course, our proffered solution simply falls apart. We're going to soon pick back up with our exhilarating mini-series on hypothesis testing of a single proportion. You are not going to want to miss that. And that's it. That's going to do it this time around. Thank you very much for tuning in. I really do appreciate it. And don't forget to stay tuned for more Quant Slob.